Okay, so my name is Steve Lentine. So I'm working for Chesapeake Aerospace supporting Goddard Space Flight Center's Code 591, which is actually attitude control. So that's kind of my background, and over the past two missions working on NICER and JEDI, started to dip my toe into the flight software development through this Simulink interface layer. So this is just a brief history of the SIL. So Ames created the original version for the Lentine mission in partnership with MathWorks. And then back in 2013, Goddard kind of forked it and started our own version for use on the NICER project. So we completed the software development for the NICER mission in 2015, and that is currently waiting for launch. And we're currently using our version of the SIL on another mission called JEDI, which is going to be launching in 2018. And so in the time that we've had our version of the SIL, we've been working with MathWorks to add a couple of features to it. And so those features are, we added CFE get time support. We added the ability to do conditional message sending. We added model reference support and multiple table support, which we're almost done implementing. And I'll go over what each of these kind of mean in a slide or two here. And then from the recent telecons we've had with Ames, and I'll let Craig comment if I got this wrong, but they've been adding some support for telemetry and commanding databases and some usability improvements. So Craig, I don't know if you want to speak to any of those or.
I can speak to some of the enhancements I guess we've had in the future. Yeah, I can speak to those.
Would you like to do that now or wait till after my?
Yeah, why don't you go ahead and go?
Sure.
And then I'll add in some things later.
Sure. And so as Dave mentioned, we're back in contact with Ames and are looking towards merging our two branches of this into something more generic for the wider community. So just to go through how this has been working at Goddard. So basically, we've been the purpose of this, I guess the SIL, the Simulink interface layer, is a set of generic wrapper code which allows us to take algorithms and code developed in the MATLAB Simulink environment and auto-generate C code, which we can deliver to the flight software team as a CFS application. And so the way we've been working this workflow is that the pointing system team develops the software requirements in partnership with the flight software team. And that has a little bit of an advantage because the pointing system team tends to be a little bit closer to some of the hardware and some of the top level like mission and performance requirements since they're the ones generating the algorithms to meet those. But these requirements are considered flight software requirements, and so they're tested and verified as part of the build and release testing for the missions by the flight software testers. And so the fact that the pointing team is developing these algorithms has a couple of advantages. We get to reuse existing GNC Simulink libraries, which have heritage. We can also reuse most of the code or all of the code. As an attitude analyst, we tend to create what we call high-FIs or high-fidelity simulations, which we use to model the system or the instrument that we're developing to ensure that we're going to meet our performance requirements. And so the fact that we can take those high-FIs and the algorithms that we develop in those and use those to generate the pointing control, for example, flight software. And that also allows us to do some earlier testing on those algorithms as we're developing them in our simulation environment. So yeah, the pointing team generates the C code, we deliver it to the flight software team, which integrates it into the flight software releases for that mission. And we've done this successfully on Lentine, NICER, and JEDI so far. And so here we have a kind of a context diagram. So you see the top orange box, the top left orange box there is what's delivered by the pointing team. So that's generated from the MATLAB Simulink code that we're developing through the auto-coding process. We come out with all of the source and header files that we need. We hand that over to the flight software team. The purple dashed box there represents the SIL. So that's the Simulink interface layer. And so the purpose of that is really, that's a generic set of software that provides the interface between, or the glue code between the CFE and the application-specific tasks. So I'll go into it in a second, but we've customized how the MATLAB Simulink autocoding processes work to produce an interface header file, which tells the SIL the configuration of that model-specific code or that mission-specific code, and handles all the interfaces between the CFE and that code. And so you can see we've got interfaces in here to get the spacecraft time, to tap into CFE event services, to handle the software bus I/O for that application, and also to manage the table for that application. And so here are kind of the components of that workflow. So we start with the model. So this is developed in MATLAB Simulink by the analysts, and contains all the task-specific code or the mission-specific code for that application. And I'll go over this in a second, but we actually have a library provided by MathWorks that allows us that has a block set that we can use in our Simulink and will provide our code functionality once it's plugged into the CFE architecture. So from there, we've worked with MathWorks to produce this TLC file, or Target Language Compiler file. And that is by and large, out of the box, what they use for their normal C generation. The customization is in the generation of that header file, which tells the SIL what the interfaces to our application look like. And then finally, we have the Simulink interface layer, which is the glue code between the code that we've generated and delivered in the CFE. And so I'm going to run through kind of how we access that CFE functionality. So the first part, this is an enhancement that we made on the Goddard side, is the get time. So in the simulation environment, this returns the simulation clock plus an epoch. But once you've generated the code, it actually makes the call to CFE get time and returns the current spacecraft time for use in your algorithms. We also have there an FTC reporting block, and so this block feeds into a packet generated by the application, which gets sent to Limit Checker, so that you can monitor the status of your hardware and software. We've also pictured up there the CFE event block, and so this, with the application of the signal, can generate a customized CFE event message, which will show up on your ground system screen if it supports it. And you can also include values from the software indicating the state of the software in those messages right from the Simulink code. Another enhancement that we've added to the Goddard version is these conditional messages. So previously in the SIL, every message was sent out at a fixed cadence. Whatever cadence, every time your app executed, it produced all of its output commands and output telemetry. And so we've added the capability with this block to control specifically when you send out those commands and telemetry, so that you can subsample your commands and telemetry, or you could do asynchronous commands and telemetry from these applications. And then the last part of the interface is the table definition. So we could actually use the CFE table services functionality to load a set of software parameters into our application and access those from our code to customize gains, for example, flags which control how the software execute, anything that we might need to change on a regular basis on orbit. And so one of the other enhancements that we've added on the Goddard side is, in addition to just using table parameters to specify these tables, we've also added support for what are called Simulink.parameter objects, which is kind of the paradigm that MathWorks is moving towards for modeling the complex data types in the Simulink environment. And so we support using those for a single table right now, and as I said, we're in the final processes of adding support for these applications supporting multiple CFE tables, so that you can partition your software parameters a little bit more easily. And there at the bottom there is just a quick description about how you can reference those in the code. So in terms of the code generation, assuming that you have your algorithms developed or a baseline of your algorithms developed, the initial setup for this process is you choose the custom TLC file so that we generate that interface file, and then you set up the data type sizes for the hardware that you're going to be running on. And after that, you just clicked build, and out pops a set of code which you can send over to the flight software team for integration into the mission software. And then on the app compilation side, there's some initial setup, defining the interfaces, assigning app IDs for the messages, adding the app to the scheduler and telemetry output, optionally defining a table validation function. But beyond that, as long as the interfaces don't change, you're just dragging and dropping the generated code over and compiling or recompiling the app. And so this also gives us the ability to do some software in the loop testing. So with a set of stubbed off CFE headers, we can compile and run this generated code in the Simulink environment. And MathWorks also supports some real-time environments such as Simulink Real-Time, which we can run this code in. And this is a description of what we used it for on Nicer. So Nicer, we kind of started small. We just coded the pointing control functionality to get an idea of how this process worked and how comfortable we were with it. So we coded a controller for our 2-axis gimbal system, including some of the sensor data conditioning and the generation of the commands to our hardware to close the loop. And so for Jedi, we did more or less the same thing, coding those pointing control algorithms, but we also took on the role of coding the data ingest. And so that's ingesting the telemetry packets from our hardware, from our star tracker, from our gimbals, from our GPS, and extracting the data that we need to use to close the loop on that. And so that's all I've got. I don't know if, Craig, you want to add anything on the AIM side, or if there are any questions that we can answer.
I had a question on, typically when you've been using this, I'm playing a little bit of catch up because of, this is from Pat, who's been heading this up. I started the initial. When you create additional CFE apps, is it a single application or is it a number of applications?
So the way we've been using this is we've been using this to generate a single pointing control application for Nicer and Jedi.
Okay.
There's nothing to say that you couldn't use this in the SIL to create a number of apps in the CFS for a particular mission. But we didn't find reason to do that. All of our functionality worked pretty well as one application for these missions, but there's no reason you couldn't do that in general.
Okay. Just going a little bit back, when we first started, we were strongly told to start to use model-based generation. And so for our first hover test, which we started this, is that we created pretty much about 80% of our entire model was all based in Simulink. And so we quickly, when we were trying to move to CFS, is quickly trying to figure out a way to do this efficiently. And model and code generation from models was something that we really wanted to emphasize. The time it was the whole autocode issue that we were trying to establish. And so that's why we worked with MathWorks in order to try to get this going. I think at this point there's a lot of similarity, and what I'm trying to look at right now is I don't want to talk about the lineage, but there is a fair amount of overlap right now. Some of the things that we're trying to do is to do the same kinds of, we're looking at usability, and that is the whole auto generation incorporating to CMake and make files, and just trying to make this a little bit more turnkey and easier out of all of this. Currently in development is some of the same things, and that's why I didn't want to. I know that Pat has been in conversation with you and with Goddard, so I don't have those particular notes, but it is again going back to the event services, the limit checker, and just a better overall integration of the messages into an overall the tools and within the CFS components. We are trying to build in some of the ideas for multi-rate messages and asynchronous messages, and so those are the pieces that I'm not sure how much is in collaboration with your efforts. So, but it has been something that's been overall very useful. So. Is that something, is Pat working directly with you at this point? Pat Castle?
So we've had a couple of telecons over the past couple months and are looking to start working more closely together and potentially merge our two versions of the SIL back together, because it sounds like we've developed some of the things that you guys are interested in and you guys have done the same for us. So
Yeah. And maybe in some small subsets to solve some of the same problems. But yes, it would be good to have a single version as we move forward. So, well, I think it'll make it easier for everybody.
definitely.
Any questions? I'm not sure what the mic.
So I heard a couple of mentions of subsampling or multi-rate. Is the Simulink interface layer currently being used in any sort of multi-rate situation? So you might have one application that has to run at a high rate and another application that runs at a low rate. Is that being done anywhere? Is that being done inside one application, separate applications? How does that work?
So right now that we're using it again, so for example for Jedi, we're auto-coding one app which contains all of the pointing control functionality that we need. But as part of that app, we do have multi-rate messaging. So for example, we control our actuators at 10 hertz, which is also the rate that the app is running at. But we also need to command our star tracker, which we do a little bit slower at 1 hertz. So we are doing that, and we also have some asynchronous messages, sending out a message in response to a command we receive. So we're doing all three of those with the conditional message sending block that I showed from Simulink.
Okay, so all of that lower rate scheduling, the 1 hertz in the star tracker case, is actually happening inside the Simulink application itself.
Yeah, I mean, in terms of, you're limited to integer multiples of the rate that your app is running at, but you can subsample in any way that you'd like.
The other way that we've done this in the past is to have multiple applications each running at different rates. And that was a little bit of why I was asking that question. So that is always another possibility to do that. The asynchronous is the one that's been a little bit trickier, and that we are still working on solutions for that.
So this might be a little bit off topic, but I'm just really curious as to how successful your auto code is, and wondering if do you use it as is on these missions that flew? Have you been using the auto code from the Simulink as is in the flight software over and over again? Like if a change is needed, you regenerate. Another change is needed, you regenerate. And do you suck that in without mod to the flight software? Or is there a team of flight software people working frantically behind the scenes to get it to work? I'm just curious.
Yeah, so the workflow that we've settled upon is that the pointing team is delivering these software. So whenever a change is necessary, we make it on the model side, do any tests that we need to do, and then redeliver the code. The reason we do that is if you start making changes on both sides, you start running into problems with making sure those changes get propagated back upstream. So the way we've been working it is that the pointing team that's generating these algorithms has it in source control, and so it flows to the flight software team so that we can more easily manage that.
Okay, so your testing and everything is done against the models then, instead of the generated code and code inspections and all that business. It's not done against the generated code.
So
Yeah.
we do both. On the algorithm side, the pointing team validates that we're getting the performance that we were looking for in our high fidelity simulations. During the development process, we also have other dynamic simulators. So for example, we have the Goddard Dynamic Simulator, which runs in the flight software lab and provides a model of the interfaces to our hardware for the flight software architecture. And so we do model comparisons between GDS and our high fidelity models. But in the end, we write in partnership with the flight software team, we write the software requirements document for this application, and they test and verify all of those requirements. So we're doing testing on both sides. The one on the pointing side is more performance and algorithms driven, and the one on the flight software side is more functional requirements driven.
We take a slightly different approach, but I would agree with some of the with the same results. Is that we use the code as is. For Laddie, we actually had integrated, and that was probably our larger effort, we had actually integrated the models into the overall code base so that, and we could have weekly builds that we could go through, and that would generate the code from scratch and then actually build the model and run all the validations. So by the end of this process, we could then take a look at the results, both the GNC team and all the flight, and also the C&DH aspects, and take a look and verify that everything was running properly. We did look at do code coverage and checking and things of that nature against the code, but what we found was that the generational tools were so good that we really didn't need to check those processes. It's kind of like checking a compiler. We usually don't, at some point you end up trusting it. As we moved forward, we tended to generate the code a little less often just because you needed all of those tools available for anybody who was doing the builds. But I agree, it actually gives you a better sense of coverage in that you can have the GNC folks test, looking at the models, and there's a high confidence that the models that get generated will be just like flight code. I mean, there's always a check also to make sure that the models in runtime, in real time, are giving the same results as what Simulink is telling us what's going on. But that, to me, is a subject of V&V for the model itself, not necessarily for the process.
And to throw in another comment from the Goddard side, NICER and JEDI are both, I guess, NICER's Class D and Class C. These are instruments on the space station. We use code generation for 2 previous missions on MAP, which was actually Matrix X. And then we did Simulink. We didn't use a SIL on SDO, Solar Dynamics Observatory, which I can't remember when that launched. But there we did run unit tests and code inspections, so we went through, those were Class B missions, and we went through the whole 9 yards. But the tools were also less mature then, so as they keep maturing, and now that these were lower class, we did do it a much more rapid cycle, right?
Very relevant. I just made a decision on my team. Well, yeah. So, yeah, I don't know if I should say it out loud. Okay, yeah, I'm. So we just started a Class A project using CFS at Johnson for the Orion camera optical nav, and all the developers there are GNC people, and they're very. They have all their algorithms in MATLAB, and I have to make a quick decision. What do we do? Do we trust the generated code for Class A, or do we not? Or do we do double work, or can we save work? And I'll just say that I decided to do all the code inspections on the final code and use UT assert to do the full coverage and basically not trust it. But that's not the answer I really wanted. So I'm encouraged to hear that it looks like it's becoming more accepted, because I don't want to do this forever, maybe.
One of the things, yeah, we did that until we felt like it gave us the results that we were expecting. I mean, to tell you way back in the day, it's like looking at a compiler to make sure that it's actually generating the code that you're expecting. But after enough of looking at that, we did feel that it was giving us the results that we were expecting. The one thing that I would add to that we did is that there is a model inspector that is within Simulink. What it does do is it does change your GNC folks to be coders. And just like you can write good or bad C, C++, or whatever other code, you can write good or bad Simulink models. And so what we ended up doing is running that inspector against those models to verify that they are following a guideline. And there's a number of different ways of doing that, and I'd be happy to talk about that at another time. But those are some of the presentations that where Karen Gundy-Burley just showed at some of the previous flight software workshops.
Yeah, and I will say we shared some of those same concerns when we were starting this for NICER, not having done it with these tools before, which is why we decided to verify the requirements with the generated code rather than the models. But having worked with that process for a couple years now on 2 missions, we've never seen a case where the model behavior differed from the code that we got out the other side. So,
This is Mike Aguilar. I have 2 comments. Number one, all the instrument side of the JWST telescope that's going up was all generated code, 100%, not just GNC, not just flight dynamics and whatever. And we started out by analyzing in essence, the software bus frameworks and triggering effects and how it interfaced to VxWorks. And then we ran static analysis on the entire thing, the code-generated code and our developed code. But as time progressed, it was one of those, we don't have enough time, we better trust kind of thing, which is what your linker and loader and compiler end up, and object libraries end up being. At some point you have to deal with that, code. I mean, I remember the days when I didn't trust the machine code, so. Second comment, did you find any problems with scalability with Simulink in code generation? Did it get slower and slower and slower as you built the model? Or is there a particular way you build a Simulink model, like you said, a good way of building a Simulink model, such that it compiles rather rapidly? What was your timing on developing this modeling? I'm speaking to just anybody that's got a project that they did that was reasonably large.
sure. So in our experience, we haven't had any issues with code build time or code compile time. It's really the simulation time. And the more complex a model you build, the longer it takes to simulate. So there are good coding practices and there are bad coding practices for Simulink, which can affect the performance of your model. And so following those helps to alleviate some of that. But the more complex the model in general, the longer it's going to take to simulate.
We had to, I would agree yes, I would agree with that comment. The one thing is that we had to finally break down from having nightly builds to going to weekly builds, weekly full builds, just because the overall process of running everything just took that much longer. But the code generation wasn't really the slow part. It was the checking, it was the modeling, it was verifying everything. That was the thing that took the longest part.
I have a back channel on that. I'll probably get in touch with you guys because I'm having some Simulink model problems with code generation that I'll probably want to pick on you guys for at least some input.
The other place to go is to use MathWorks. They're very good. They understand this, and they are also a good resource, but I'm happy to help.
Yeah, same here. We've been working with MathWorks through their pilot support program to develop these additional features that we've added to the Goddard SIL. And so they're very supportive in that endeavor.
Okay, thanks, guys.
You have a great processor and lots of space. I don't know if you really care, but is there any concern about that? I mean,
yeah. So I guess on Nicer and Jedi, we haven't. Our processor and the complexity of our code has been such that we haven't run into a problem with that yet. So I don't know.
We run on an older Rad 750, so I mean, you can't get. That's pretty typical. And we didn't have a problem. I mean, there were issues that we had to balance out of all of this, and there are some other possibilities. But overall, we haven't had those levels of performance problems.
Yeah,
with
we
the
haven't either.
generated code.
I would say the Nicer software was relatively simple for us. Jedi, we're kind of taking a step up in that in addition to doing the data ingest, the processing of the raw data that we're getting, we're also, for example, doing onboard orbit determination as well as our control. And so even with those algorithms in place, we haven't run into a problem.
and what processor do you have there again? Is that a Rad 750 or?
I will have to check on that.
Oh, it's the VR, the broad reach.
Yeah, it's broad reach.
Right.
So it's a 404, a 405.
Broadreach 405 is what we're.
But isn't that similar to a Rad 750?
Yeah.
I think it's clocked a little higher. I think it's like 400, 200 or 400.
Okay, thanks.
Yeah, so I think the processor is faster on that particular one.
Paul, did you happen to measure your margins on that? Do you know what your timing margins were?
We do, the flight software team as part of our CDRs does report that during that. I don't have that off the top of my head, but we had no problems for NICER, and we just went through CDR for the flight software for Jedi also with no problems. So
For Lati for flight, we had about 30% processor usage. I've got to say the code generation that comes out of the models, we took a look at it, for sort of reasonability. It's again one of those, looking under the hood and really seeing what goes on. And the code generation was very good, was very efficient. Now there's a few different code generation products that come from MathWorks, and so we were looking at the embedded coder. And that particular one, we were very happy with the results. I mean, that was a reasonably good coder would have written that code. So, and there were some optimization flags that we tweaked and tuned. That's probably the biggest sort of thing, is setting everything up with the right flags. But once we had that, then everything worked great. And that was, again, Lati was probably 85% all generated code.
So I just take the opportunity to share a bit of experience we had from the European Space Agency on this topic. And indeed, we have Criticality B software that has been auto-generated through the tool chain that we have been talking about, so MathWorks and Simulink. I highlight that you need to be a tool expert to actually create the good software. So it's no longer about saying it's auto-generated, but you need to actually demand to use the embedded coder. You need to have quite strict rules on how to configure the tool to get the correct code out. And you need to, our experience is that whoever is having the opportunity to create the auto-generated code needs to have quite some limitations around what to create. For instance, in our cases, there was just a asynchronous process, so it was not a dynamic software, because the dynamic behavior of the software itself is provided by a scheduler that is outside of the auto-generated code. So in principle, you create auto-generated code that is plugged into architecture that's already available. So that was a way to actually constrain or to limit what the auto-generated code can do, as well as whenever that code has to be maintained, you maintain the whole executable of that code. So there are certain, decisions or agreements up front that we have seen that is necessary.
Okay, I guess I got one follow. Craig, did you guys do anything with the database from the modeling into the ground, or is that all just hand generated later?
Yeah, that's our Skimmy. That's really our tool. It's our Django tool that we use for managing all of the different data, and that's including the buses, the tables, all the other CFE messages from all of the other things, and it generates, both the files for Simulink as well as the right header files and ITOS pages and everything else. So that's what. But yeah, so that was what our tool is designed for, as well as any other interfaces such as electronic data sheets and things of that nature.
Okay, thanks. Okay. Thank you. Thanks, Craig.
Thanks.